All right, so we're going to review the immune system stuff we've already covered. We're going to try to finish up most of the rest of it. Obviously, your immune system is there to protect you against germs like bacteria, viruses, but there's other stuff: fungi, worms, protists, all kinds of things. The most simple part of your immune system is the non-specific, or sometimes it's called innate, which means innate means like built in, right? Almost like instinctual. And that includes the skin, which is obviously a barrier, blockade. But the skin also is active. It makes chemicals that help kill germs, like sweat, for example, has urea in it, which is toxic. How do we make urea as a byproduct of what? Protein. Our livers will convert what more toxic chemical into urea? No, try again. Ammonia into urea so that we can hold on to it a little bit longer without having to urinate all the time. You also have inflammation. When there's damage in a certain area, your cells basically release this cell signal, which is like an SOS signal. And the main one of those signals is called histamine. What does histamine tell the blood vessels in an area of damage to do? Dilate. So you actually send more blood to damaged areas. More blood, though, means more what? More platelets and also more what? More white blood cells to help kill off any infection that might be there. You also have interferon, which interferes with virus reproduction. You have stomach acid. Pretty much everything that comes in through your mouth gets killed by your stomach acid, so that's a good thing. Denatures proteins. You have the normal flora in your body. Normally, flora means what? Plants, but in this case, it means what? Bacteria. The ones that line your digestive tract. The ones that live on your skin. The ones that live in the female reproductive system. They're sort of like blockers. They keep other things from growing there that shouldn't be. Now, if you get on antibiotics, you not only kill whatever you're trying to kill, but you also kill these things. And what can that lead to? Yeah, secondary infections like diarrhea or yeast infections or other kinds of problems. Your saliva and also your tears have inside them this chemical called lysozyme, which obviously cuts or splits or breaks germs, kills them. Your mucous membranes are really good filters, help to get rid of things before they get too deep inside your body. And you have these things called pyrogens, which actually cause you to get a fever. Fever is actually a good thing. Your immune system works more effectively when your body's a little bit hotter, and it helps you get rid of the infection faster. So by getting rid of the fever, you actually are probably prolonging the infection. You feel better, but you're going to be sick for longer. Those are just a few of the parts of what we call your non-specific immune system. That's not what we're here for today. Today we want to concentrate on the specific part, or sometimes it's called the acquired part, which means you have to what? You have to gain it through experience, through battles. You have to fight battles and hopefully win them. That's how you build up this immune system. Now, two key words to note: antigen and antibody. What is an antigen? Any foreign protein in your body. And when you get a foreign protein, whether it's from a bacteria, a virus, a protist, a worm, somebody else's kidney that they gave you, whatever else it might be, what does your body make in response to having these foreign proteins inside you? You make your own proteins called antibodies. And these antibodies float around in your blood and they sort of act like smart bombs. They attack only that particular way. Antigen, and they stick to it. And they can help you get rid of that antigen in a number of ways. One way is by causing those antigens to clump up so they're easier to get rid of. One is basically by acting like a mark for death. What are the real killers in your immune system? Macrophages. They're kind of big and dumb and slow. And they're just kind of wandering around aimlessly. But if a germ has a big sign on it, in this case an antibody, a big mark for death saying, hey, here it is, the macrophage would come and help you get rid of it pretty fast. And then another thing that they can do is they can act sort of like a handle. They attach to that antigen, and other parts of your immune system will grab onto that antibody and escort that germ to where? Your kidneys, where they'll be filtered out and you'll urinate them out. And that's why your doctor tells you to do what if you've got a virus? Drink clean fluids so you can flush them out. So let's talk a little bit about how this whole antibody thing works. One part of your specific immune system, the part we've already talked about, is antibody-mediated or humoral. Now, why do we say this is called humoral immunity? It only is effective in the fluids of your body. Antibodies are these big old bulky proteins. They can't get where? Through membranes. Yeah, they can't get through membranes. So antibodies aren't going to help you if the virus is already where? Inside a cell. Antibodies can't help. This part of your immune system only helps if the germ is in the fluids or between the cells. Can't get into the cells to kill germs that are already in there. All right. Typically the way this works, and I'm going to go to a diagram and talk about it. Eventually I'll get there. Let's start here. The antigen is in your body for the first time. A macrophage. We'll just kind of accidentally bump into it. And what do we call the macrophage? What the macrophage does to it? Again? Phagocytizes it. And then it performs what process on it? Before that. Intracellular digestion, where it'll break it down into pieces. And it'll take a few of the antigens from that germ, and it'll put them outside on its own cell membrane. And that's called antigen presentation. And the piece of the cell that actually holds up that thing like a trophy hand, what's that called? Yeah, an MHC class II protein. Here's where cell signaling comes in. It's holding up this piece of the protein. Sort of like what we see in this picture right here. And what is this cell that will come in and dock with it? It's called a helper T cell. And I said it sort of goes Helen Keller on it. In that the fact that it's filling it and it's filling the structure of that antigen, it's becoming familiar with the antigen. And then once the helper T cell is stimulated, it's activated by this. What does it then act like? I compared the helper T cell to what historical figure? Paul Revere. It's the helper T cell's job to send out the message. Not only the germs are coming, but the germs are already here, and here's what they look like. Go kill them. That's what the helper T cell's job is. Now, if we go back to this other slide for a second. So these helper T cells specific to that particular antigen, this is a specific immune system. These are specific for that one germ, send out their own cell signals called interleukins. And what does that mean? Between white cells. And those messages go out and stimulate other helper T cells that are of that type. And they also stimulate a type of cell called the B cell. These cells are really important. Once the B cells are stimulated, B cells that are specific for this one antigen, they start to clone themselves really, really fast. A lot of those cloned B cells become plasma cells. And a plasma cell is essentially a factory for making loads and loads of what? Antibodies specific for that one antigen. But a few of those B cells don't turn into plasma cells. A few hang around as memory cells. So that if you ever get that infection again, what happens? You kill it before you even get symptoms. See, it's really fast the second time around. But this is what we call antibody-mediated or humoral immunity. It's great for killing germs that are where? Outside the cells, in the body's fluids, like the blood or the fluids between the cells. It can't get into the cells to kill those kinds of germs. So we'll get to that other part in a minute. Let me back up just a touch to begin with, though. Something we talked about, we've been talking about in class lately. When they first started doing the Human Genome Project, how many genes did they think they would find? At least thousands and thousands. They found way less than they thought. And it turns out for making antibodies, we only have a few genes. And how many germs are there? Yeah, maybe not infinite, but a bunch. We only have a few genes. But what do we know about our genes that we didn't know a few years ago that would help us with this issue? Each gene can code for multiple things. They can be, what can happen to them in different ways? It can be processed in different ways. So that, remember that these antibodies have to be specific. They have to fit to the germ. This whole RNA processing and splicing thing, though, alternative processing and splicing, allow us to make millions and millions of different types of B cell receptors, or antibodies in this case. Remember, though, that the antibodies have to be specific for the antigens. It's sort of like a lock and a key fit together. Here's what an antibody looks like. If this little site right here does not specifically fit to the antigen, that antibody won't work. Looks like a lot like an enzyme and an active site, or maybe like a ligand and what? A receptor. They have to fit. Here's some ways antibodies can help you out. Like we said, antibodies are proteins. They're made to attach to very specific antigens. We said they might act like tongs, that white blood cells can grab on to a dangerous germ and transport it again to where? The kidneys, and flush it out. Here's sort of what happens in your antibody-mediated response. Specific B cells get activated. Most of they then start to clone themselves. B cells that are specific to that germ. Most of those cloned B cells become plasma cells. And they're called plasma cells because they have huge amounts of the roughy R in them. Why would that make sense? Antibodies are proteins. Proteins are made by ribosomes and rough ER, so it makes sense that cells are making a lot of protein should have a lot of rough ER, right? Remember, though, that some of those cells stay behind as memory B cells. These pretty much last forever. But once the infection's over, what happens to those plasma cells? What again is apoptosis? They kill themselves. They commit suicide once the infection's over. But these memory cells hang around, and if you ever get that same infection, they'll help you get rid of it pretty fast.
So would there ever be a chance for your memory cells?
There is a chance that some of them could die, but that typically doesn't happen. They're just floating around watching. Think of them like security guards. Mall cops. Yeah, those are your mall cops. Let's talk about the other kind of immunity, the other kind of specific immune response. And that's called cell-mediated immunity. And we talked a little bit about this before. We'll get a little more specific now. We said that the only cells in your body that have that MHC class II protein on them are what kind of cells? Macrophages and other cells that do what? Through phagocytosis. Only phagocytic cells have those MHC class IIs. But every cell in your body has a protein called what? MHC class I. And what are they constantly digesting from the inside and then putting out on that MHC class I protein? They're proteins from inside themselves. And if everything's okay, what kind of proteins are going to be up there? Just typical cell proteins. It could be either one, potentially. But let's say the cell has mutated and is now cancerous. What's probably going to be floating around inside that cell? Some I proteins. Or maybe that cell's got a virus infection inside it. Probably some virus infections are going to end up there on the outside, right? So this MHC class I protein is sort of hey, here's how I'm doing inside kind of thing. It's sort of like a doctor takes a little scope and looks inside your ear. That's basically what the MHC class 1 is showing. Here's what's inside me. And coming around to check that are helper T cells. So here would be this would be a normal body cell right here. This would be its MHC class 1. And then here's that helper T cell attaching again, doing Helen Keller imitation. And if it determines that the protein that it felt is weird, what's it going to do? Well, helper T cells don't really do much killing. We said they're sort of, again, like who? They're like the Paul Revere. So here's what's going to happen. Again, antigens are displayed by infected cells. Maybe they're virus proteins, maybe they're cancer proteins, but they're displayed on the MHC class 1 in this case. The helper T cell will come into contact with that. They'll stimulate these cells called cytotoxic T cells, or sometimes they're called killer T cells. Cells specific to that antigen are stimulated. Wherever there are these antigens sticking up on cells, these things go. And once they get there, what do? They go Wolverine on those cells. They flip out the claws and they poke the cell. They kill it. All its guts leak out. Hopefully before what happened? Hopefully before what cycle was finished? The lytic cycle, because otherwise it didn't do any good to kill the cell, right? If the lytic cycle is already finished. We want to do it before the lytic cycle is over. That helps to kill your own cells that are infected. So that's a way to treat what we call, what's the prefix for inside? Intra. So cell-mediated immunity is a way to treat intracellular infections that are already inside your cells.
Enzymes to loss and actually have like a structure.
They have enzymes to do it. And again, once this is all over, you have memory cells, and you also have the active cells that do the killing. So these are the killers. You also have basically memory cytotoxic T cells. But if you ever get that infection again, you can get rid of them before it gets too serious. So one more time, antibody-mediated immunity or humoral immunity helps to get rid of germs that are floating in your body's fluids, between your cells, in your blood. Whereas cell-mediated immunity helps to kill specific germs that are intracellular, inside. But both of these are specific. Both of these target very, very, very specific things. Does that make sense? All right, let's look at one or two other things here before we go. Let's look at this diagram here to begin with. Now this is using this in terms of an immunization. I'm just going to talk about it in terms of you got an infection. Say right here at day 0, some new virus that you've never had gets into your body. Well, what does your body start to do? Slowly. Takes a while for it to figure out what it is. It takes a while for it to find the right types of cells to deal with it, the right helper T cell, the right B cell. Once it finds the right one, then what does it have to do with those B cells and helper T cells? It has to clone them. And then the B cells have to turn into what? Now, what are the cells that make the antibodies called? Because they have so much ER, they're called the plasma cells. That takes a while. So my point is, once you first get an infection, it takes several days, maybe a week, maybe more than a week, for your antibody levels to really start going up. And you see the antibody levels go up very slowly. By the time your antibody levels get up to the top, what's probably the case? By the time they cap out up there at the top, the infection's probably over. And so what starts to happen pretty quickly? Antibody levels drop back down. And notice they'll never quite go to 0. The first time you get an infection, your response to that infection is called the primary response. It's kind of slow, and your antibody levels never get very high. So you have sort of a slow, weak response the first time you're exposed to an antigen. That's why you actually have what? Symptoms. That's why you get sick. But let's say right in here about day 60, you're exposed again to exactly the same thing you just got over. What do you have floating around in your blood? Even though you have very few antibodies, what's still floating around? Memory B cells, memory helper T cells, memory killer T cells. They're all there. They know what that germ is. They know how to target it. They know how to kill it. So the second time, and the third time, and the fourth time, and the fifth time, and however many times you're exposed to that infection, it's called the secondary response. And what do you notice about that secondary response? It's much what? It's much, first of all, faster. It happens almost immediately. And what happens to your antibody levels? They are much, much higher than they were the first time around. That's why typically the second, the third, the fourth, the fifth, the sixth time you're exposed to that same antigen, what doesn't happen? Yeah, you don't typically get any symptoms. Because this response, the secondary response, is so much faster and so much bigger. Does that make sense? Let's backtrack and look at something else here.
Waited 2 hours Tuesday, Wednesday.
Really? Amazing. It's gonna be cold.
It's gonna be cold. Wow.
Yeah, I know. I don't understand. Yeah, they couldn't do it when it was 10, but they're gonna do it when it was 9. Or I don't understand the logic. Guess that's. I don't think it has to do with the snow. Tiny, tiny. Anyway, congratulations on the delay. Let's talk a little bit more about immunity here first, though. There's 4 main types of immune responses. First one is natural active. Let's think about that for a minute. Natural active. This is a normal immune response. This means how'd the germ get in you? Naturally. And what did you do once it got in you? You actively fought it off. So you caught a germ through some kind of natural process. You actively fought it off. So what's left behind? Yeah. What's left behind when it's all over? Memory cells. Which means the next time you're probably not going to get wet. Sick. Another kind of immune response. How's it going, Steve? Good. Good. A natural passive immunity. What might that be? Natural passive immunity. Let's say we're talking about babies. How might they get natural passive immunity? They never got sick. How'd they get immunity to a particular germ? They could get antibodies from where? How? Say a baby who's already born. Breastfeeding. Okay? Breast milk has antibodies in it. Provide immunity. That's why breastfed babies tend to be healthier than bottle-fed babies in terms of they don't get sick as much. Also, there can be antibodies passed through the placenta from a developing baby, from the mother to the developing baby. But that's natural passive immunity. You get antibodies in some natural way, either through breast milk or through the placenta from your mother. Yes. That's why HIV-infected mothers aren't supposed to breastfeed and that kind of thing.
So in the case you are breastfeeding, what would you do?
If you were sick with some serious infection.
I mean, I know this is formula.
I mean, more than likely, by the time your symptoms showed up, you've already given it to the baby anyway. So you probably should continue giving them the milk because you will make antibodies which you will then pass on to the baby. What would artificial active immunity be? This would be how immunizations work. Vaccinations. They inject you not with the real virus, but with what? Sometimes it's pieces of the virus. Sometimes they've taken the germ and they've deactivated it somehow. They just inject you with specific what? What's a specific piece of a germ called? What's the word we use over and over today? An antigen. They inject you with specific antigens. That's how it works sometimes. Now, they also sometimes can give you a live virus that's been weakened. Sometimes they can give you what are called attenuated vaccines. For example, let's take the flu vaccine. How do they grow that? How do they prepare that flu vaccine? They take a human flu virus and they inject it into chicken eggs. And they let it grow inside the chicken egg. And then they'll suck some of that out of the chicken egg, they'll put it in a different egg. They'll let it grow for a number of days. And they move it from egg to egg to egg. As it's living in those chicken eggs, it's becoming less good at what? Infecting humans, but more good at infecting chickens. So it's evolving, essentially. But by the time they take it out of the however many eggs they're going to use, it's still enough like the flu virus. It still has some of the same, what? Okay, but what's the key word? It still has some of the same antigens as the real human virus. So if they inject you with that attenuated, that weakened version, if you ever encounter the real thing, what happens? You still have memory cells and antibodies that will kill it before you ever get sick. That's attenuated. What would artificial passive immunity be?
You're given a specific antibodies.
You're actually given, through injection, specific antibodies. You guys, all of you were supposed to read, and hopefully did read the Hot Zone. What did the African doctors try to do at the end that the CDC didn't want them to do to treat the people with Ebola?
Inject them with other patients.
Yeah, they took blood from people who had lived through Ebola, and there weren't many of those, right? They took some blood from the people who lived through Ebola, and they transfused that into people who still had Ebola, thinking what? That blood should contain memory cells more than anything that knew how to kill the Ebola quickly. And what happened in the case? Turned out it worked. The people they did that with lived. What were the CDC people and USAMRIID people afraid of? They were afraid they would give them something else, like HIV or malaria or some other blood-borne germ. So instead of getting rid of the Ebola, they were afraid they would kill them with something else. So they didn't want to do that. But artificial passive immunity, taking antibodies, memory cells from a patient who's lived through the infection, and then giving to someone who currently has the infection. I mean, it wouldn't be practical in most cases to try to treat it this way. Something really serious, maybe. But it just wouldn't be very practical to do in those situations. Right. And there aren't that many people who've had Ebola, so it'd be tough to do. All right, the last thing that I want to mention, and then I will let you go, are autoimmune diseases. And autoimmune disease is when what happens? Your immune system starts to attack itself. And typically, who gets these? What group of people typically gets autoimmune disease? It's almost always women. There are some men who get them, but it's usually women. And it's also usually women who have done what? Had children. And there's some people who think that, while you're pregnant, you sort of have to slow your immune system down and tolerate a little bit more stuff inside you than there ought to be, right? Because you got this artificial life inside you that has different antigens than you have, and you don't want to kill it. So you temporarily sort of have to hold back your immune system. And there's some people who think that autoimmune systems happen when that confuses your immune system. And it has a hard time telling self from not self. And it gets confused. And a lot of times they think that you might have a virus or a bacteria with antigens very similar to your own. Like strep sometimes, strep bacteria. Sometimes have antigens similar to human antigens. And that your immune system starts killing the strep, but then it confuses the strep antigens with your own antigens, and it starts killing you too. There's a lot of these out there. Maybe the most famous one, type 1 diabetes. Who tends to get type 1 diabetes?
Children.
Children. And this is when, for some reason that we're still not sure of, your immune system starts to attack what organ in your body. Your pancreas. It starts to attack the hormone-making parts of your pancreas so that you lose the ability to make enough insulin. Some others, rheumatoid arthritis. Now this is not regular arthritis when you have sore joints. This is when your immune system is attacking your joints. You've probably seen people with this before. Their fingers are all like twisted and bent, like gnarly fingers. You guys know what I'm talking about? Their knees are all crooked and twisted and turned. Their joints swell up. They bend and twist at weird angles. Very, very uncomfortable. Debilitating. You can't lose the ability to do anything with your hands, essentially. Have a hard time walking because of the knees. Multiple sclerosis. In multiple sclerosis, the myelin sheath. What's the myelin sheath? Yeah, that's the insulation around nerve cells. It gets attacked. Think if you had a wire going through your body, an electrical wire without any insulation on it, running through water. It would short out all over the place, right? That's essentially what happens here. So that when your brain is telling certain parts of your body to do something, the message never makes it to where it's supposed to go because the insulation is not on the wires anymore. So you start losing control of certain parts of your body. You can't consciously control them anymore.
What's the name?
He has amyotrophic lateral sclerosis, which is, in some cases, somewhat similar to this, but much more severe than this.
Like, Christine House, or like, Christine House, right?
Okay.
So they always get some lupus.
Yeah, that's what I was about to say. Lupus is the weird one. Lupus has all these weird symptoms. It starts maybe as a rash, you get kidney problems, sometimes it can be digestive issues. A lot of times if a doctor like House can't figure out what's going on with, they guess lupus. Because lupus can show up in so many different ways, especially if it's a woman. That's going to be one of their first guesses if they don't know, well, maybe it's lupus. Because they have just weird symptoms. And then one final thing I'll mention, and then I'll call it a day. Immunodeficiency disorders. HIV, AIDS. The HIV virus wipes out what part of your immune system? The helper T cells. Which means there's no Paul Revere. So your immune system doesn't know what. It doesn't know the germs are there, and it doesn't know what they look like, and it doesn't know how to kill them. So even though the rest of your immune system would work, there's no central kind of cell signaling them to go work. So essentially, what are you left with once you have a full-blown case of HIV in terms of your immune response? You're left with those non-specific things like skin, inflammation. You don't have any tools to specifically kill germs anymore. They're gone. That could happen. And then one other one that I'll mention, last thing I'll mention is SCIDS, severe combined immunodeficiency disorder. This is genetic. This is the genetic disorder that the boy in the plastic bubble. You guys seen that movie before with John Travolta? It's a disease that he had. That was based on a true story. It's very rare, but essentially you're born without a working immune system. And if you're not put in some kind of plastic enclosure, germ-free enclosure, you will die very, very quickly from some kind of simple infection. We'll say one other quick thing: stress. Stress causes your body to make all kinds of hormones, right? Mostly hormones from what gland? Which is your stress hormone making gland? Think. Everybody in here knows this answer. Because of the big one that it is. What is it? The adrenal gland, right? Like the adrenaline is a stress hormone. But you also make lots of other hormones, specifically a category called corticosteroids. And one of the side effects of corticosteroids is what? Weakening your immune response. So stress can make you sick because the stress hormones weaken your immune system's ability to function. If they were to give you an organ transplant, one of the things that you might have to take, corticosteroid shots. The same things that are made essentially by your pancreas or by your adrenal gland when you get stressed out. Kind of scary. Pretty much finishes up the immune system. We will call it a day there, and I guess I'll see you late tomorrow.
Don't forget.